All right, good morning, at least for me. This is chapter 15. This is on ring homomorphisms. So interestingly, even though when we did group homomorphisms and group isomorphisms, we spent a fair bit of time on both of those. Here we won't so much. It's actually not as necessary for where we're going, which isn't to say it's not as relevant in the grand scheme of things, but for us, not so much. So this brief intro, we can really think about this as sort of a quick look at ring homomorphisms and the ramifications. Let's say ring homs and uses. And so I'll sort of break this into a couple of sections. So we'll do basics. So I'll give a few definitions, give a few examples, and then I want to talk briefly about the First Isomorphism Theorem, how it applies to rings, things like that. And so you'll see a lot of parallels here with what we did with groups. So basic definition. So we'll say if R and S are rings, so then a ring homomorphism so this is a mapping from R to S, which basically preserves both of the two operations. So this is a mapping, let's say phi from R to S, such that two things are true. Phi of A plus B is phi of A plus phi of B, and phi of AB is phi of A, phi of B. And again, just to remember that the first operation, this operation, and this operation, those are in R, but this operation, this plus and this multiplication, this is in S. So coupled with that, we have two associated definitions. We can add in a ring isomorphism. So we're doing this actually in reverse order from groups. In groups, when we did we did an isomorphism first. Rings, we're just listing them backwards. So a ring homomorphism is a ring isomorphism if it's also one-to-one and onto. And then third definition, we have a kernel, like we did before. So the kernel of a ring isomorphism, of a ring homomorphism, let's say phi from R to S. This is the set. So just like before, it's basically defined just like a group homomorphism. It's the set of elements that go to 0. So it's the set ker phi of all the things in R such that phi takes them to 0. And that 0, of course, is in S. So let's just look at a few examples. So the mapping, say phi from Z to Zn. Put that in the right place. Given by phi of x, let's say, equals x mod n. So I'm not going to, the first few of these are basic, and so I'm not going to show that they're ring isomorphisms, but I highly recommend that you try them. The fourth one is a little more confusing, so I will show it, just because it feels like it should be obvious, but isn't. Right? So in this case, this is with kernel. So it's everything that goes to 0 mod n. So it's all the multiples of n. So here I wrote definition. Sorry, this is an example. So a second example. The mapping C to C, complex numbers to themselves. Given by, so the mapping here is complex conjugation. So let's say A plus BI goes to A minus BI. This is with kernel would just be 0. So third simple example, the mapping phi from Rx, so this is the set of the ring, if you like, of polynomials with real coefficients to R, given by, we've seen something like this mapping before for groups. So I'm going to take a polynomial and I'm going to say plug in 2. This has kernel. This is everything that goes to 0. In other words, everything for which p of 2 is 0. This is all the polynomials with p of 2 equals 0, which is the same as saying all the polynomials which have x-intercept at 0. So those three are fairly easy to see. I mean, you should try working them out, see that they satisfy the criteria, see that the kernel makes sense to you. But let me go through one that's a little more confusing, and I'll explain why it's confusing. So take a look at this example. There's another one like it in the book. I'm doing a slightly different one than they do so that you have something to compare. So we'll look at the mapping phi, which will go from Z12 to Z30 given by phi of x is 10x mod 30. So both of these are addition. So it looks like you might say to yourself, so let me preface this by saying this is not obvious. So you might ask yourself something like, well, why not? Like, why can't we just write for example, for the addition bit, right? Why can we not simply write this? Phi of x plus y is 10x plus y is 10x plus 10y is phi of x plus phi of y. And so the answer is that all these additions are modulus additions. And so they take place in different places. And so there's a problem, right? So the issue is, let me mark these in red, right? Is that this guy, this is mod 12. This multiplication, let me, yeah, so actually let me be really cautious here. This addition in here, because this is the x plus y from over here, this is also mod 12. This multiplication is mod 30. And then when we distribute it, it's like we're in the new thing, and it's a bit confusing, right? This is sort of really mod 30, but the addition of the x's and y's was mod 12, but this addition is absolutely mod 30. And so the moduli change, or if you like, the modulus change, makes this non-obvious. So what we really mean is the following, right? So we really need to show that the following is true, that phi of x plus y mod 12, that guy is phi of x mod 30 plus phi of x mod phi of y mod 30. And similarly for multiplication, because that way it makes sense, right? When we add in the left hand side mod 12, that transfers over to adding mod 30. the two independent ones. Now, of course, this right-hand side, if it helps or if it makes it less confusing or more confusing, this is the same as phi of x plus phi of y mod 30. That's no big deal. That's because each of them is just existing mod 30. But either which way, we need to show that. Right? So then the question becomes, how can we do this? And so the way to appreciate what's going on here is that when we say this mapping back at the beginning, this can sort of help us a little bit right here. This is a mapping from Z12 to Z30. So we can think about the numbers that go in as numbers from 0 to 11, right? So for x in Z12, we think of, let's say we use x in the set 0, 1, up to 11. But when we do x plus y, or let's say for x and y in Z12, x plus y is not necessarily, I mean it might be in that set, but it's not. So for example, if x plus y, if you have say 5 and 7, then when you add them you get 12, and that's not in that set, but it's congruent to something in that set, congruent to 0. So x plus y may not be in this set. Yeah. So then what can we do? So this is what we do. So this is what we'll do. For x and y in Z12, we'll write x plus y. So we'll use the division algorithm. So what we'll do is we'll write this as a multiple of 12, say 12q for quotient plus the remainder. This is with the remainder between 0 and 11. So then what happens is when we take phi of x plus y, we have to think through this very carefully. When we take phi of x plus y, this becomes the same as phi of 12q plus r. Now, because 12q plus r is in Z12, inside here this is congruent to r. This is because 12q plus r is congruent to r mod 12. Now, this r is now simply between 0 and 11. When we take phi of it, we'll get 10r. That's awfully nice, right? Now, r again now, if I solve for r is x plus y minus 12q. Now, just to be clear about something, this 10r, this is now taken mod 30. This is in the target ring. This is also mod 30. This is really also, I didn't put it in here, this is mod 30. As well as here, just to be clear, because this is in the new space. This is on the new ring per se. So this now, if you observe, is the same as x plus y. Sorry, I made a little mistake here. Let me back that up. I filled in the r, but I didn't multiply by the 10. So this is 10. Then I put the r in. This is x plus y minus 12q. This is mod 30. This is 10x plus 10y minus 120q mod 30. Because this is mod 30, the 120q is 0. Right, the second part, or the third part really, here, this is 0 mod 30. So this simply becomes 10x plus 10y mod 30. And 10x, of course, is just phi of x. And this is phi of y. And this is mod 30. Which is exactly what we wanted, as desired. So now we can do exactly the same thing for multiplication. Let me put this in. I want to put it in without erasing anything, so I'm going to make it jam it a little tight here. So for multiplication, we're looking at phi of xy. And so what I'm going to do here is I'm going to do the same for xy. I'm going to write xy as 12q plus r. Right? This is phi of 12q plus r. This is mod 30. Just to clarify, what we've done here is we've put xy equals 12q plus r. Same thing, the remainder is between 0 and 11, possibly 0. So when we do this, this is the same as phi of r, because 12q plus r is the same as r mod 12, which is what's happening inside the parentheses. This is phi of r mod 30 then. Phi of r is 10r. Fill in the r again. So the same sort of thing is happening. Oops, this is x, this is xy minus 12q mod 30. So now this is a little sneakier, because if we distribute this here, so the 120q again vanishes, but we have a 10. And the 10, I don't want to get 10, I actually really want to get 10x times 10y. But 10x times 10y is the same as 100xy, and 100 is the same as 10 mod 30, right? So this all becomes, let me go back over to here. This then becomes, well, let's say is equivalent to, a lot of these are equivalent to's, and I've just been a bit sloppy here, so apologies for that. This is the same as 100xy mod 30. Again, that's because 120 is the same as 0, that vanishes, and because 10 is the same as 100. This is then 10x, 10y mod 30, which is phi of x, phi of y mod 30. And that's the end of the example. Right? So this is sort of worked out in detail because it's one that feels like it should be obvious, but isn't at all obvious, I think, given the way that it structures. And the way that you might be tempted to write it can just be wrong if you just sort of blindly wrote this statement up here. Right? That is not right the way it's written, because the modulus are all sorts of confused and changing and different in different places. So for the last thing, I just want to list a few properties of homomorphisms, and then the connection to quotient rings. And so let me clear this page off, and then the rest of it can fit on one page. And then that's the end of the section. It's a pretty quick section. So third thing, some basic properties. We had a lot for group homomorphisms. I'm not going to list nearly as many here, just a few. So we'll say these are the few critical ones that we'll need later on. So let phi from R to S be a ring homomorphism. And I'm going to let A be a subring of R, and we're going to let, let's say, B be an ideal of S. So the reason these are different here is just because the results we need are different. So this is what we get. Phi of A, this becomes a subring of S. So in other words, if you have a ring on the left, a subring on the left, it moves over to a subring on the right. Now, if A is also an ideal of R, so it would be tempting to say that phi of A would be an ideal of S, but it actually isn't necessarily. It's a homework question to give an example of one that isn't. But it is true that phi of A is an ideal of phi of S. So we can say as part of this, if phi is onto then phi of A is an ideal of S, but otherwise it's just an ideal of phi of S, of the sort of codomain, if you like, or the range rather, more specifically. So phi inverse, interestingly, of B is, however, an ideal of R, no matter what. Now, just something, don't forget this thing, I'm not saying that phi is invertible. When we write this, we have this issue with groups too. This is simply the set of things in R such that phi of A is in B. So the function may not be one-to-one. So you just take everything in the original R that gets you something in B. So D, if R is commutative, so is phi of R. S isn't necessarily, because you might miss some stuff. So E, if R has unity, let's say 1, if S is not the ring comprised only of 0, and if phi is onto, then phi of 1 is the unity for S. So F, these last two are similar to what we had for groups. So if phi is an isomorphism, or rather, let me rephrase this as an if and only if more correctly, is that phi is an isomorphism if and only if phi is onto, and the kernel is just a 0. And last but not least, if phi is an isomorphism, then so is its inverse. Now, I'm not going to prove any of these. I'm not going to prove anything in this last patch of stuff. So, because we'll be using these in very few cases, and so I don't want to obsess over them too much. But all of these proofs are actually fairly straightforward, and I highly recommend that you try them. Some of these may show up on homework, some of them may show up on the second exam or on the final, something like that. So they're all like really good exercises to try. They use the subring test, the ideal test. They all sort of work through what it means to be an ideal, what it means to be a subring, what it means to be a unity. So they're all great practice, which is why I sort of want to avoid them. The book avoids them too. It just sort of says those are all very similar to group ones. They're in the exercises, so have at them. And yeah. So last thing then is so the connection to quotient rings. So if you remember when we did the group version of this, we made this comment about how when you have a homomorphism, the kernel is a normal subgroup. That gives you the First Isomorphism Theorem, and we also get the reverse, that normal subgroups are kernels. So we're going to have exactly the same few things here. And again, without proof, we'll actually very rarely use some of these things. So this is really here, partly I think, just to help reinforce these ideas. So first theorem is that kernels are ideals. So in other words, let phi from R to S be a ring homomorphism, and the kernel of phi, this is an ideal of R. So B theorem, so this is the first isomorphism theorem for rings, fit for rings. So we'll say let, again, phi from R to S be a ring homomorphism. So I can define a new mapping, let's say psi. So psi will go from because we know that the kernel is an ideal, we can construct the quotient ring. That will go to phi of r. If you look back at the first isomorphism theorem for groups, you'll see an extremely similar statement. Then this new map given by psi of, I take an element in this thing, so an element in this thing looks like an element in the ring plus the coset, and I take that to phi of little r, that this guy is a ring isomorphism. And last but not least is that ideals are kernels. So, in other words, every ideal A of a ring R is the kernel of a ring homomorphism. Let's say is the kernel of, let's say, the ring homomorphism, because we can explicitly give it, that goes from R to R mod A given by little r gets mapped to little r plus A. So the proofs here are all straightforward. I don't want to dwell too much on them because, like I said, they're not ones that we'll use a whole heck of a lot. But they're things to sort of keep in the back of your mind. But they should also feel pretty right. What I would say is when you're focusing on these, some things to think about is over on the left, I'm going to mark this up a bit, is all of these are very much like for groups. So this is like the group version with normal subgroups. So I would say take a look at those. On the left-hand side, there are some specific ones that I would say recommend that you try first. When you're proving these, would be B is a good one, and specifically why the onto requirement is necessary in order to get an ideal. And the idea here is that when you take phi of A, remember the definition of an ideal is something that fundamentally, if you take something in the ideal and multiply it by something outside of the ideal, you get something in the ideal. So if the function's not onto, there may be things outside of phi of S that when you multiply by them, things get messed up. So same deal here. It's like, what happens if this is not onto? Right? Things in the target space can be missed, and it messes things up a bit. So I would say on the left-hand side, focus on these first when you're sort of thinking about them and thinking about counterexamples and thinking about what could go wrong. Everything else is pretty straightforward. Right? It's basically obey the definitions, very much like groups, not overly difficult and definitely worth doing. So with that, I'm going to end this section.